Hello guys, it's me, Spency, and today we are going to talk about another type of reaction balance, the extent of reaction balance. Now, I advise you that you go through the molecular species balance video before proceeding, as these two kinds of balances are very much relatable. But if you did, let's proceed. Basically, our extent of reaction balance is a simplification of our molecular species balance. We introduce now a new term called an extent of reaction, as we denote by glorious epsilon. Now, our term, now we could write our balances as out is equal to in plus the stoichiometric coefficient multiplied by epsilon. Now please note that the extent is an extensive property that is the same for all substances in one reaction. This is unlike our molecular species balance, wherein we consider too many modification terms. Now our DOF for this balance is unknowns plus independent reactions minus independent species minus other constraints. Now you may ask me, Spency, what is an independent reaction and an independent species? Well, an independent reaction are reactions which cannot be expressed in terms of other present reactions. Okay, this might prove difficult, so let us illustrate using four theoretical equations. Now let's consider the first two equations. We know that the second equation is just 4 times the first. So for these two equations, we could now only consider one of them to be an independent reaction. Now let's consider equations 1, 3, and 4. If we add 3 and 4, we would get equation 1, right? Thus, we could only consider two independent equations for these three. It could be either 1 or 3, or 1 or 4, or 3 and 4. But you cannot consider all three of them as independent equations. Now let's move to the concept of independent species. Independent species are species in a reactor which cannot be expressed in terms of other species before and after a reaction. So let's illustrate this as an example. 50 moles of A and 100 moles of B react to form 25 moles of A and 75 moles of B and 20 moles of C. Now, in the first stream, the ratio of the two substances is 1/2, unlike in the second stream, which has the ratio of 1/3. Thus, we could say that both A and B are independent of each other. Unlike, let's say, if we put B and the last stream as 50, the two streams have now the same ratio, which is 1/2. So A and B could not be considered both as independent species, but you could consider one of them as an independent species. And together with C, they could form as two independent species. So let's consider a problem. Consider the combustion of methane. If 300 moles of water enters the reactor and 400 moles comes out, what is the extent? Now let's plug into our equation, and through the power of shift solve, we could get the extent, which is 50. Now if 100 moles of methane enters the reactor, how much comes out? Now let us plug it in again to our equation. Please note that our stoichiometric coefficient is -1 due to our sign convention, and through this we could get our final answer of 950 moles. Now let's consider the extent of reaction balance pros and cons. So our first pro is that this is very efficient for multiple reactions. However, I would not say it is efficient for all multiple reactions, but I would like to say that it is very efficient because you could just write different extents for different reactions. However, if you have so many reactions, this is not very efficient anymore. Also, it is very useful for equilibrium reactions. But this is another topic, and maybe this will not come out in the exam. But I encourage you to study more behind it. It is constant for all, so there's no need to determine specific terms. So the extent is always constant for a certain reaction. So I highly encourage you to use this aside from the molecular species balance, in which you need many modification terms. One very, very strong con is that it is inefficient for complicated unbalanced equations. The stoichiometric relationship of the reaction is required for extent of reaction. So if you don't know the balanced chemical equation, well, don't use this kind of reaction balance. And again, we also have the introduction of several unknowns. Again, we are also introducing extents, and if an extent is an unknown, so it might be proved too difficult to do extent of reaction balance. Additionally, we have complicated degree of freedom analysis. However, this proves to be so much more useful than molecular species balance. So let's now use this in a chemical engineering problem. A reactor system was established so that the reactant stream, which consists of 40 moles sulfuric acid, 40% hydrochloric acid, and 20% potassium hydroxide at 1000 mol per hour, will react through the equations shown below. If the effluent stream contains 375 moles per hour sulfuric acid and 300 moles per hour hydrochloric acid, determine the complete composition of the effluent stream and the percent conversion of potassium hydroxide, the yields of potassium chloride and potassium sulfate, and selectivity of potassium chloride over potassium sulfate. So now, let us go to our calculation chamber and let us start solving. Hello guys, so we're now back here at the calculation chamber where we will solve the problem using extent of reaction. So again, as we defined, extent of reaction is basically using the equation such as out is equal to in plus the stoichiometric coefficient times the extent of reaction. So like any good engineering student, we should start off with the diagram. So if we're going to draw it here, we know that what goes in is 400 moles of H2SO4, 400 moles of HCl, and 200 moles of KCl. What comes out, all we know is 300 moles of HCl and 375 moles of H2SO4. I hope this is the making of the diagram is clear. I'm sorry if it looks any less than beauty. Anyways, let us solve for the extent of the two reactions. So we have two reactions for this system. We have KOH plus HCl creates H2O plus KCl. Then the other reaction we have 2KOH plus H2SO4 produces 2H2O plus K2SO4. Now we have these reactions, so I'm going to label extent 1 and extent 2. So we could get extent 1 by doing a balance on HCl. So out is equal to in minus the stoichiometric coefficient, which is 1, because it's reactant, so it's negative, minus 1 multiplied by extent 1. Thus, we could get extent 1 as 100. Are we clear? Clear. Alright. Next, we're going to do a balance on H2SO4 to get the second extent. So that's 375 is equal to 400 minus 1, again because it's a reactant, extent 2. Thus, extent 2 is equal to 25. Alright, so we have the two extents. So let's calculate for the remaining compositions. Now, we're going to use NKCl we're going to calculate for the KCl next. So we know that KCl only is generated using the first reaction. So NKCl is equal to 0, which is N times plus the stoichiometric coefficient, which is 1, multiplied by the first extent, which is 100. Then we do that the same for K2SO4, wherein which is equal to the second extent, which is 25. Then we should use this for NKOH, which is equal to the initial amount, which is 200, minus the first extent, because it's a reactant, minus the second extent, because it's also a reactant. Negative 2 because that's the stoichiometric coefficient here. So that's approximately 50. Then you have your NH2O. It's produced in both reactions, so that's 0 plus E1 plus 2E2. You get 150. So this now becomes your composition. Next, we are asked to determine the percent conversion. So it's a basic plug and play. Conversion is basically 200 minus 50, over 200, which is 75%. Then we use selectivity, which is 100 over 25. because it's KCl over K2SO4, which is 4. Then we have the yield of K2SO4, which is equal to 25 divided by 100, because if all KOH is used to produce K2SO4, it will produce 100 moles of K2SO4, theoretically. So that's 25%. And lastly, for KCl, 50 moles, divide by 200, divide by 100, because if all KOH consumed goes to KCl, we will produce 200 moles. Oh, sorry, I totally mistaken. This is supposed to be 100. So 100 divided by 200 is equal to 50%. So these are our statistics if we are to use extent of reaction method. As you could see in our previous video, this is also the result for molecular species balance. Thus, we conclude that both balances are very, very accurate. So, yeah, that's it for extent of reaction. It's quite easier than molecular species. So that was our video, guys. Thank you for watching. If you want to subscribe to our channel, you could do so with the logo above. And if you want to check out for more 101 videos, you could click on the video down below. Thank you for watching, guys, and good luck on your long exam.